Alpha, how na dey? All right. Good evening, everyone. Yeah, so great. Hope you guys are doing well. Yeah. Okay. So we're good to go, right? Last night we went into probability distribution function, and we spent our time on Bernoulli distribution. We also talked about binomial distribution, and I believe you guys have a great idea on what those two distributions entail. Now, if you recollect, I listed out 4 different distributions under probability distribution function that we'll be considering. The first being by Bernoulli, the second being binomial, the third Poisson, the fourth geometric. All right. So these are the the 4 distributions we will be spending our time on, and I want you to understand that every of these distributions have their various features, and for you to be able to answer questions on all this, you must be very conversant with what each and every one of them has, what their feature is. So last night we talked about the features of Bernoulli and binomial. I told you guys that Bernoulli has a peculiarity, and that's the fact that it has to do with just one trial. This is a one trial event. One trial. While binomial, very similar to Bernoulli, but it has n trial. Right? Now, we're going to a different one, Poisson. So you have to be very, 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 very great at understanding what's the feature of Poisson, so that when you see a question, because I need to tell you guys that in many cases, they will not tell you that this is a Poisson question or this is a binomial question. You will be the one to be able to interpret that. Looking at what we have here, I'm very certain that this will be a Poisson distribution. All right. So this is where we want to start from, Poisson distribution. So what is Poisson distribution? Of course, as you could tell, Poisson distribution is a discrete probability distribution because we are still on that probability distribution function. Once we delve into probability density function, that will be the moment where we'll be talking about continuous distribution, continuous probability distribution. So this is still all on that discrete. These 4 are on that discrete, all right? So Poisson distribution is a discrete probability distribution. I'm sure you understand the use of the word discrete there already. You already know how to differentiate between discrete and continuous, all right? We have spent time on that in the past, so we will not spend much time on that today. Now, what is the peculiarity in Poisson? Poisson expresses the probability of a number of events occurring in a fixed period of time. Let me say that one more time. Poisson expresses the probability of a number of events occurring in a fixed period of time. Now, I understand that some of you you heard that, but you could not really put your hands on it. We said probability, we said it expresses a probability of a number of events occurring in a fixed period of time. If you look at this definition, it should be enlightening enough. Number one, expresses the probability of a number of events. I'm sure you understand where that's coming from. Probability of x equals to 2. That's what that first thing is saying. Expresses the probability of a number of events occurring. Now, this is the real key that makes you to understand if you are dealing with Poisson or not. When you see a question that has something to do with a fixed period of time or a fixed space, maybe a fixed distance, a fixed volume, you will see, I'll give you examples very soon. When you see something that has to do with, when you see questions that has to do with relationships like this, where you're talking about the number of something in a particular time, the number of something in a particular space, the number of something at a particular distance or volume. When you see something in that light that expresses those things, understand, number one, that that's going to be a Poisson. Now, one other thing you will be always seeing when you're dealing with Poisson distribution is that they will be giving you something which we call the average rate. Don't worry, I'm going to come back with everything I'm saying. The average rate will be given, or sometimes you may be told to find it, but the average rate is always in consideration when dealing with Poisson distribution. So we say that Poisson distribution expresses the probability of a number of events occurring in a fixed period of time if this event occur with a known average rate. So this event we are talking about must have an average rate. The event we are talking about here, we said it expresses the probability of a number of events. This event we are talking about must occur with a known average rate. Now, this known average rate is always expressed as lambda. This is how we express the average rate of Poisson. So let me come back again, because I understand this is the first your first exposure to this. Poisson division expresses the probability of a number of events. Probability of a number of events occurring in a fixed period of time. Now, this was, of course, fixed period of time, but I wanted to relate that to, it could also be not just time alone, it could be space. Like, let me give you an example. Imagine you are counting the number of occurrences of an event in a given unit of time, distance, area, or volume. See an example now. The number of car accidents in a day. The number of car accidents in a day. The number of hibiscus flower in a square meter plot of land. If you can understand what I'm saying, when you're talking about something occurring in a particular fixed period of time, or fixed space, or fixed distance, once you're seeing questions that mirrors that experience, where you are hearing the number of car accidents in a day, let me quickly say one thing to you guys. There's no other distribution we're going to be talking about that has this peculiarity. So you would have to even do too much to identify a Poisson distribution, I can assure you. because no other distribution has this experience in what all the four we're dealing with here. Every one of them have their peculiarity. I told you already that Bernoulli is one trial. You will see it when you see it. One trial with two possible outcomes. Binomial is n trial with two possible outcomes also. They are very similar. Now, Poisson, it's not any of all those ones. Although I'm going to give you very soon the relationship between Poisson and binomial. There's a relationship that comes between Poisson and binomial, which I'll be expressing to you sometime in this class. Now, Poisson, its own peculiarity is that it's always having the feel of something around a fixed period of time. The number of car accidents in a day, a fixed period of time. You see, you had to fix a something, not just the car accident occurring. All these other ones, we didn't have all those peculiarity where we are saying the number of something in a day or in a square meter, in an expanse of land, in a square meter plot of land, per square inch, per minute, the number of phone calls per minute. If you understand, all those things that has to do with having an experience of those, know already that that's going to be a Poisson distribution. All right. Now let me read out an example now that is perfectly a Poisson distribution. Look at it now. 1 nanogram of plutonium will have an average of 2.3 radioactive decay per second. You can see, once you see questions like that has to do with something, a number of events occurring in a fixed period of time. I told you already that even though this is a good definition, this could also be mirrored to distance, area, volume. It doesn't have to always be time. So look at the question now. You see a question that says 1 nanogram of plutonium will have an average of 2.3 radioactive decay per second. When you start seeing that fixed period of time, of course, you would also be able to, they will always, in all cases, talk about an average rate. If you are dealing with Poisson distribution, you must always have a way of either getting or you would have been given an average rate. Because if they say something occurs, like let's say you drive 15 kilometers per hour. If you understand that, average rate will exist in that situation. Average rate, all right? So you will be able to talk about an average rate. So everything that has to do with fields of that form, just know already that this is going to be a Poisson distribution. It's a very interesting distribution and one of the most commonly, because it's broad in application, and it's very broad in application. So you would have to be it's very simple to understand. So you have to be very great at it. It's very simple. So everything I've said is everything about it when it comes to understanding how to recognize questions. That's just all about it. Once you start seeing something that has to do with per second, per minute, per square meter, and all those things, that obviously is telling you that that's going to be a Poisson question. All right. Can you please indicate if you're following me? Okay, good. So now, of course, just like in every other case, we can always, we should always have what we call the PMF. Don't forget, just to recollect, just for the sake of revision, for that of Bernoulli, we said probability of x equals to x was equals to p raised to power x, 1 minus p raised to power 1 minus x. That's the PMF for a Bernoulli distribution. For that of binomial, we said it was p equals to of course, this equals to n combination x. We said p raised to power x, then 1 minus p raised to power, in this case now n minus x. And your x is ranging from 0, 1 up until n. Very, very important that you always know all this. Now, let's get to that of a Poisson distribution. What's the PMF? What's the PMF of a Poisson distribution? For a Poisson distribution, the PMF, of course, this is a discrete random variable, or a discrete distribution function. So the PMF is very unique, different from the rest. It's gotten as e raised to power minus lambda, lambda raised to power x over x factorial. It's quite unique. This is x factorial. So you need to be very conversant with all these PMFs. They are very much important. You cannot do any question without them. So please be very pay real attention to this. Now, again, don't forget, I always want you to know whatever all these things mean. So let's quickly talk about the representation of everything you have in this formula. First of all, let's talk about lambda. We have said so much around that already. Lambda here is whatever in your question represents the average rate. So when you see any question in an exam hall and you are sure this is a Poisson distribution, the first thing you want to bring out is, what is my lambda? Your lambda is so key, so key to getting anything on Poisson. In short, there's almost nothing you can do on Poisson without lambda. You can see that lambda is used here. Lambda is used here. Now, that's that about that. So you'll be able to recognize the lambda once you can pay attention to whatever the question was saying was the average rate. So if they say something occur something per second, then you obviously know that's the average rate already given in that place. So when you're told to, like for instance, the question I read that said something will have 2.3 radioactive decay per second. So you know in that case now that lambda there is going to be 2.3, because 2.3 per second, that's the rate, that's the average rate. So if they say 1.3 per hour, all right, that's the average rate. So okay, so you can, let's also talk about the other aspect of the formula. And you can see this E right here is something you have on your calculator, exponential, all right? Exponential is something you press on your calculator. This is not something you will get from the question. This is something you will get from your calculator. So if your lambda was 1.5, you will use your calculator to press, you will be pressing E exponential raised to power minus 1.5. Of course, doesn't mean it cannot be gotten by workings, but there's no need to say so much around that, because this is better gotten. Whatever your lambda is, just E raised to power 1 is, I believe E raised to power 1 is 2.718 or thereabout. So, but you don't need to start trying to solve that yourself. Just press this on the calculator and you get the answer. Whatever your lambda was will bring about the answer here. Now, this x now, of course, that's, I believe x is the last thing we need to talk about. X as just like in the previous distribution, x will be representing the events, the successes, all right? So if you are told to, for instance, what's the probability that in a 2 second period there will be exactly 3 radioactive decay? That means 3 radioactive decay happening. That means the success of 3 radioactive decay. So in that case, your x is still representing the number of successes. It will be, so if we wanted to solve that question, I will be saying probability of x is equals to 3. So the number of successes based on the question you are solving. So without further ado, let's delve into examples. Now, before we get into examples, I need to specify what is the value for your x. Now, your value for x, now, in this case, you don't talk about number of trials. Let me tell you that. You can see that we have not said anything around number of trials because this is not something that has to do with trials. N trials, 2 trials. This has nothing to do with trials. This is, as I said, number of events occurring in a fixed period of time. It's not about trials, so you don't have N here. Yeah, but you can now be talking about what's probability of having a certain number of events in probably a particular period, maybe in 2 minutes or in 2 hours, depending on whatever the question is saying. So that's what your x here is representing, the successes. So if I say what's probability of having exactly 4 radioactive decay, that means 4 there will represent the success. All right. So your success will obviously, when you are trying to state this formula, will be from 0, because it's possible to have 0 success. That means it's possible that there was no, in that case question I was reading, it's possible there was no radioactive decay. So success could be 0, it could be 1, it could be 2. So, but since all this will depend on whatever question you're dealing with, we cannot specify the last possibility of what the success value could be. So that's where we'll just say x is from 0, 1, 2, and on and on. This will all depend on whatever question you're dealing with. This don't have anything to do with trials. So it's possible for them to ask you what's the probability of having this number of events in 10 seconds. Sorry, what's the probability of having 10 radioactive decay? So in that case, 10 radioactive decay, your number of success will be 10. So if they say what's the probability of having 2 radioactive decay, your x there will be 2. This is what's the probability of having 100 exactly 100 radioactive decay, your x there will be 100. So this value for number of success will be based on whatever the question is saying. That's why we don't have a lasting point. Different from that of a binomial. In binomial, the number of success will be based on the number of trials. You cannot have number of success exceeding number of trials. So if you have 20 trials, you cannot have 21 success. It's not possible. That's why the band of your success was between 0. It's possible to have 0 success, but the last will be n, depending on the number of trials you have. So if you have 20 trials, you can only have 20 success. It's quite very simple. So now let's quickly talk about the mean and variance of this distribution. So the mean of a Poisson distribution, this is a very, very, very unique distribution. And let me quickly tell you guys, it's a very good objective question. They can ask you that what distribution function has both its mean and its variance as the same thing. All right. So this is a unique distribution because both the mean and the variance are the same thing. And what's the mean and variance? The mean and the variance is lambda. So this is a very unique distribution. If you ask to find a mean, the mean is whatever lambda was. If you ask to find the variance is still lambda. All right. So obviously, you know that the standard deviation in this case will be the square root of lambda. All right, because variance is standard deviation is square root of lambda. All right. So standard deviation is square root of variance. So if variance is lambda, then that means standard deviation will be square root of lambda. So this is what you need to know about Poisson distribution. The next thing we have to do right now is to go on to solve lots and lots of questions. So guys, brace up now. This is the time for you expressing yourself mathematically. Okay, so guys, I want you to shoot your answers very soundly. All right. So with everything I've said now, I believe you have a very proper introduction to Poisson distribution. Now, the very first question: a machine produces the first thing I will be asking you is to recognize your average rate. But of course, in this question was more direct. So, but let's start with the more direct one. Then later on, you will be able to bring out the average rate yourself. To find the probability of exactly 3 defects in 1 hour. Now, pay real close attention to this question. The question said a machine produces defects at an average rate of 2 per hour. I'm sure you understand what defects are. That means probably, let's say the machine was producing sandals. So, of course, machines, even though they are very great, but they are not always so perfect. There's always something we call defective items. So now we are being told that a machine produces defect at an average of 2 per hour. So in an hour period, you will see 2 defects. So the question says find probability of exactly 3 defects in 1 hour. Now, look at this question. Nobody will tell you this is Poisson, this is not Poisson. You would have to recognize it from the feel of the question. I told you guys that Poisson has to do with expressing the number of events occurring in a fixed period of time. Sometimes it could be space, it could be area, and whatever, as I mentioned already. If you look at the question like this, you are hearing per hour, per square meter, per this. You already know that this is a Poisson distribution. Now, of course, you can see that this was very explicit. Average rate was said. They did not minus word here. Of course, not every question will give you it as direct as that. At an average rate. So we're told here that the average rate, which I told you was what we represent as lambda, is 2. So the average rate here is given as 2. So the question says find probability of exactly 3 defects. Exactly 3 defects. That means in this place now, your x is equals to 3. I told you that x represents the number of success. So the probability of exactly 3 defects in 1 hour. Now, guys, I need to state one thing. This question is direct, but not every question will be as direct as this. The average rate was given 2 per hour. The question told you to find 3 defects in 1 hour. Guys, if they told you to find 3 defects in 2 hours or 3 hours, your average rate cannot be 2 for this question, for this solution. Let me explain that. The average rate initially given was 2 per hour, If they ask you to find the probability of 3 defects in 3 hours, you would have to multiply the lambda with 3, because in this case now we're no longer dealing with just, to answer this particular question of exactly 3, if they said in 3 hours, your average rate, you cannot use the average rate of, you cannot use the average rate of 3 in 1 hour to solve for this. You have to multiply that by 3. All right. So note that, but in this case, you are very lucky. The question was very direct. It said at an average rate of 2 per hour. And the question said 3 defects in 1 hour. So you are good. That's why we're using it directly. All right. If it was in 2 hours, we would have multiplied this our lambda by 2, because these 2 hours we cannot use the average rate for per hour for 2 hours, because the average rate will change. For 2 hours, it will be 4. If it was 2 per hour, that means it will be 4 for 2 hours. So that means our average rate when we are trying to answer the question, if this was 2 hours, would have been 4, not 2. If it was 3 hours, it would have been 6, not 2. So note that. But in this case, everything is intact, so we can easily move accordingly. All right. Good. So now, uh, let's try and solve this. When you look at this question, you know exactly that. You know this is obviously uh, a Poisson distribution. So you can easily produce the PMF. I will try and rewrite the PMF as many times as possible as I normally do so that you guys can get familiar with it. So this is the general PMF of a Poisson distribution. We have e raised to power minus lambda, lambda raised to power x over x factorial. This is something you have to know. This is not something that is going to come differently. You just have to know it. Right? When you write it often and often, it sticks to you. Now, the question is for you to find x being 3. The probability of exactly 3 defects in 1 hour, that will be x equals to 3. Of course, because they said 3 defects. 3. I told you already that this represents, when you say exactly 3, and x represents the number of successes. So in this case now, we are talking about, this will be e raised to power, our lambda is 2, minus 2. Lambda, that's 2 raised to power, our x is 3, raised to power 3 over 3 factorial. That's what we have to solve. When you're done solving this, of course, this is everything here. It's not something you have to crack your head on. You can go on to push this on a calculator directly, and you will get your answer quickly. So I'm sure that if you solve this on a calculator, you should get your answer to be 0.1804. That's simple. So this is how you tackle questions on Poisson distribution. It's this simple. Every other thing now after this will just be technicalities, maybe removing one, asking you to find the other one. But this is the entirety of Poisson distribution. At this point, if you have understood this, trust me, you are very good to go. But of course, to consolidate your knowledge, we need to solve more questions. Take this question quickly and start to solve it. Mean, I'll just write it here, please. Mean number of accidents equals to 4 per week. All right. So the question is, find the probability of no accident. You can see how funny this question is. Nothing is being told you on if this is binomial. They just said, oh, mean number of accidents is 4 per week. Find probability of no accident, and that's all. Mean number of accidents is 4 per week. Find the probability of no accident. Someone that is not familiar with all these things I said before now will be very stunned, like, what does this mean? What can I do here? It will look like a very difficult question. But when you see a question that has something that has to do with, as I said already, a fixed period of time or space or whatever, when you see something of that form, you know this is modeled as a Poisson distribution already. So when I see a question like this, I know this is a Poisson distribution. And you guys, of course, I believe you know how we do it. You can go on to be solving. That's very important. So it's very good if you apply your hands to work while I'll be doing mine also on the board. So the mean number of accidents is 4 per week. Of course, average rate. I told you that average rate is what we call lambda. And another word for average is still mean. So when you say average rate equals to lambda, and you see mean number of accidents equals to 4 per week, so you know already that lambda is equals to what? 4. All right, lambda equals to 4 in this case. So the question said you should find the probability of no accident. Find probability of no accident. No accident means, in this case, the number of success, which we call x, will be equal to 0 because no accident, x here is equals to 0 because they said no accident. No accident. If they said find probability of 3 accidents, or 1 accident or 5 accidents. If you see questions like that, obviously you know that your x will not be 0 there. But probability of no accident means the accident number of accident there is 0. So your x there will be 0. So obviously you know already. So you know already that this is a Poisson distribution. So you're going to be using the probability mass function. All right. This is the probability mass function. As I said, I will try and write this over and over again so that as much as possible you can get conversant with it. Now, fixing this all in, we are solving for probability of x equals to 0. That will be e raised to power minus 4, 4 raised to power 0 over 0 factorial. I'm sure you guys are very good at all these things. E raised to power minus 4. Then 4 raised to power 0 will be 1. So this will be times 1. 0 factorial is 1. So this answer will disintegrate to e raised to power minus 4 as the only thing. So this is the only thing you'll be pressing on the calculator, e raised to power minus 4, because e raised to power minus 4 times 1 is this over 1 is still this. So this will be 0.0183. Are you seeing questions that students will see in the exam and feel it's so difficult? Are you seeing how simple it is? This is, I told you, you know, I would not lie to you guys. This is everything about Poisson distribution. People, you miss this question, it's only because you probably don't understand the basics. It's so simple. This is everything. So once you pay attention to the basics, you cannot go wrong. So let me give you this. Another one. This one, of course, you know, we're going to increase the technicality in this case. Still very simple, but again, I don't even see any technicality in what I want to write. But all right, let's see it. If you are told now, if lambda equals to 3, you are told to find the probability that x is less than or equals to 2. So look at the question. If lambda equals to 3, find the probability that x is less than or equals to 2. So this is something you need to pay attention to. And the major thing is in this word less than or equals to 2. All right, this is the key there. This less than or equals to 2 makes it something you need to pay attention to. But again, it's still very simple. If you have been following all our conversations around probability, it's going to be very simple for you. Now, can anybody write a word problem for saying this without saying it with this mathematical expression? Can anybody write it in a word problem way? Which other way could they have said this? Which other way could they have said this? Could you have gotten this question in word problem? Can anybody give me an answer to that quickly? Tell me a word problem way, because even though you are seeing this expression mathematically, but there's a way they could have said this with words that you would have to decode what they're saying. Thank you very much. I like that person. At most two. At most two. At most two. That's the right way of saying. So this is another way of saying at most two. At most two. That's the perfect answer. At most two. Meaning, what they mean by at most, or whatever you have here, is that x can be equal to 2. X, but it can be equal or less than 2. That means x will be equal to 1. But I have always told you, this is one of the pitfalls of students. When they talk about x being less than or equal to 2, people always do for 2 and 1. Some people, ignorant ones. You must always involve the 0 part, because 0 is also a possibility. Less than or equal to 2 involves when it's 0 also. So these are the 3 probabilities that is embedded in this question. At most 2, or x less than or equal to 2. So you go on to add this, because the meaning of this is that probability of x less than or equals to 2 means it could be probability x equals to 2, or probability of x equals to 1, or probability of x equals to 0. So you have to go on to solve this. All right. Go on now and solve this. All right. So now this is a great exposure. At least you get exposed to how to solve this. So you want to solve probability of x equals to 2 plus probability of x equals to 1 plus probability of x equals to 0. Now, so that you don't ask me, do I need to arrange it from 2 to 0? You can arrange it from 0 to 2 anyway. That doesn't matter. So what you'll be doing here is, obviously your lambda is given as 3. Since lambda is 3, and don't forget the PMF, just in case you are forgetting, let me write it again for you. The PMF for Poisson is e raised to power minus lambda raised to power x over x factorial. So this is what we're going to be using for every one of them. So we have e raised to power for that of when x was 2. X is 2 now. So you know that when x is 2, you'll be putting your x as 2 in all this expression. So we have e raised to power minus, don't forget your lambda is 3. So everyone will have e raised to power minus 3. That will be generic to every one of them. Then lambda raised to power, now lambda raised to power x, but your x is 2 in this case. So that will be x lambda raised to power 2 over 2 factorial. That's for this. Plus, for when x was 1, the same thing, because lambda is still going to be the same. Lambda is 3. That's the average rate. So in this case, you have 3. You have lambda raised to power. Now you'll be having your x as 1, because we're doing it for when x was 1. 1 factorial. Following the same thing, we'll do for that of 0. E raised to power minus 3. Then lambda raised to power 0 over 0 factorial. So you guys should go on and solve this. Can you give me the answer for this first? What's the answer for this? Okay, it looks like you guys have pressed this all in a calculator. Of course, you will get an answer for this. You get an answer for this. You get an answer for this. Then you add it up together. So that's just it. I believe the answer you're going to get will be 0.4232. That's simple. Are you seeing how simple and straightforward these questions are? Very simple. All right? Very, very simple. Again, when you are starting to learn something, sometimes it may take a while for you to grasp the whole concept. So don't beat yourself too hard. You are still at the initial phase. Actually, I think you guys are actually very smart if you have gotten it at this point, because that means you're very intelligent. So just keep at it. And if you are yet to get it perfectly, just keep following. We keep solving enough examples. Very soon you'll get familiar with what's going on. So don't give up on anything yet. All right? So look at this question. This question is something that has to do with reverse psychology, reverse engineering, reverse arithmetic, whatever you want to call it, where they will need you to move from the back to the front. Normally you're supposed to move from the front to the back. They give you lambda, you put it in your probability mass function, and then you get an answer. But yeah, look at what they are telling you. They're telling you the answer already. They want you to reverse this to give whatever was lambda. You understand the whole concept to this? So that's what they're asking you to do here. So they are telling you now already the answer for when probability of x was 0. They are telling you the answer already. So they want you now to move this to the front. All right? So they said probability of x equals to 0 is 0.1353. Find lambda. So how do you solve this? So very simple. Of course, once you have understood this, when you see lambda here, you obviously know that this is a Poisson distribution, and you know that the PMF is going to be given as probability of x equals to x equals to e raised to power minus lambda raised to power x over x factorial. Now, you know this already, but now they are telling you that probability of x equals to 0, which will mean if you're going to put this into it will mean e raised to power minus lambda. You don't know lambda raised to power 0 over 0 factorial, because you know if you're going to put it, the only thing now is that you don't know your lambda, but they told you that this was equals to 0.1353. If you look at what's going on here, they gave you the answer for the probability, but they didn't give you your lambda. So you are going from the known to the unknown. So it's very simple. All you need to look out for here is, now that you have gotten this right here equals to this. So look at it. E raised to power minus lambda raised to power 0 over 0 factorial is equals to 0.1353. What is lambda raised to power 0? Anything raised to power 0 is going to be 1. So this is going to automatically turn to times 1. What's 0 factorial? 0 factorial is 1. So you see that all this will get into e raised to power minus lambda equals to 0.1353. All right. So how do you find this? What do you do next to get your answer? It looks like some of you have gotten the answer. What did you do next? So you take the ln of both sides. Exactly. So you take the natural logarithm of both sides, and when you do that, you're taking the ln of both sides, you'll be getting lambda equals to the ln of this will be 2, approximately 2, right? Somebody is asking if I can explain how to press it on the calculator. Of course, there is that on the calculator. You look at, you see it there, it's written on the calculator. You see a place that is written like ln. It's on the calculator, probably towards the top right, depending on the calculator you're using anyway. Okay, so I'm going to ask this question. I'm going to see who is going to get this one. Very simple also, but you have to be smart, because if you take this on face value, you may not be able to get the right answer. So look at the question. The question said if lambda is equals to 5, so you have to find the probability of x greater than or equals to 2. This is the question. So look at this question now. For those of you, if you look at this question, can anybody give me a word problem for this word? What would this question have said if it wasn't going to write it with a mathematical expression? What are you going to see? Yeah, thank you very much. At least 2. The word there is at least 2. So at least 2, because if you can look at this, they are saying probability that x is greater than or equals to 2. Greater than or equals to 2, so it can be 2. But it must not be less than 2. It should be greater than 2. So 2, 3, 4, and so on. You can see this statement embodies the word at least 2. At least. The least should be 2. All right? Good. So how do you solve this? That's a very important question now, because I want you guys to be very good at what you do. Now, if you look at this question now, you will be confused if you have to put this on face value and just solve it the same way we have been solving, where you want to go on to say, okay, I want to find the probability of when x was 2 plus probability of when x was 3 plus probability of when x was 4 plus probability of x when x was 5, and so on. Where are you going to stop in? Where are you going to stop in? This is going to be very almost impossible. So that's why you have to be very smart. and you have to use the concept of complementary events. I told you guys when we're dealing with complementary events, I told you that it's a very powerful tool. It helps you to solve complex questions very easily. So now look at this question when you have probability of x greater than or equals to 2. Look at all this. This is endless, of course. But don't forget that there is an easy way you could have approached this. Remembering that there is the complement of this thing I highlighted here now will be 1 and 0, because that's the only thing not in this set. So the only thing not in this set of 2, 3, 4, and so on and so forth, is 0 and 1. So this plus 0 and 1 will make the whole universal set, obviously. So you can see that 0 and 1, probability of 0 and 1 represent the complementary event, the complementary probability of every other of this particular set of elements. If you can understand what I'm saying, guys. So now, instead of you going on to solve probability of x equals to 2 or probability of x equals to 3 and so on and so forth, you will go on to solve for probability of x equals to 0 and 1 or 1. So then you will say 1 minus that probability. So this is what I'm saying right here. So you will say the answer to this, to find probability of x greater than or equals to 2, which is very difficult to solve. You do for 2, do for 3, do for 4, do for 5. Just imagine how crazy that could be. You have to be pressing for each of them. So all you have to do is to go on to solve this expression. To get this one, you will say 1 minus probability of when x was less than or equals to 1. And that will mean 1 minus probability of x equals to 1, or probability of when x was equals to 0. So this is how you solve it. So look at it. Normally, if you didn't do it this way, you would have to be saying probability of when x was equals to 2 plus probability of when x was equals to 3 plus probability of when x was equals to 4 plus probability of when x was equals to 5. Where are you going to stop in? So instead of going on to solve all this, knowing the concept of complementary event, that two complementary events will add up to get 1. I believe we have talked about that before. An event plus the probability of an event plus probability of an event complement will give you 1. So if you're trying to get like this event now, since you can easily get this event, this is easier. Just find the probability of 0 or 1 is easier to find. So if you find the probability of that, subtract it from 1, you'll be able to get the probability of this one. I'm sure you guys can follow. So go on to solve this now. Find this and then subtract it from 1. That will be the answer to probability of x greater than or equals to 2. Okay, so of course you don't need to sweat this. All you need to do is to recollect your PMF. I'm sure you recollect your PMF. I've told you I want to write it as often as possible so that as much as you can, you are recollecting it. That will be e raised to power minus lambda. Lambda is power x over x factorial. So to get this, you'll be dealing with e raised to power. Your lambda here was given as 5 minus 5. Then 5 raised to power, your x here was 1 over 1 factorial plus probability of, e raised to power is still minus 5. Then 5 raised to power 0 in this case over 0 factorial. So this is what you'll be solving. Pressing this on the calculator. Whatever answer you get here, you subtract from 1. I believe you'll get an answer of 0.9596. It's that simple. All right, so you guys can see how super interesting this topic is. Uh, this is how simple it is. If you have been following, I'm sure you are getting more confident as the day go by. So, of course, you know my own duty is to expose you to as many questions as possible. So, calls arrive. This is another question at 1.5 per minute. The question is for you to find the probability of at least one call. So calls arrive at 1.5 at mean 1.5 per minute. Find the probability of at least one call. So this one question. Let me give another question right here. Okay, so have you gotten an answer to this? Okay, it looks like I can see the correct answer there. So just again, quite very simple. Calls arrive at mean 1.5 per minute. Of course, you can identify there that your mean lambda is equals to 1.5. All right. Find probability of at least one call. You are told to find the probability of at least one call. So at least one call. Now, I want you to know how to interpret that. At least one call. Do you write the greater than or equals to 1 or less than or equals to 1? Which one do you write? Of course, it has to be greater than or equals to 1 because this represents at least one call. So the least is 1. It can be greater, but the least must be 1. So you can have 2, you can have 3. So this is another good example of where you use complementary events because solving this question is not going to how many do you want to solve to get the answer? Will you do for 1, do for 2 because they say greater than or equals to 1. At the least must be 1. So you can have 2, you can have 3, you can have 4, you can have 5, you can have 6, you can have 7, you can have 8, you can have 9, you can have 10. Can you imagine you having to solve all those things? So what you have to do here is not to go on to solve it that way. You have to use the concept of complementary events where you'll be. In this case now, what do you think will be the complementary event of this? Can anybody tell me in the comment section? What do you feel is going to be the complementary event of probability of x greater than or equals to 1? What's the complement of this? Can I get an answer there? Now, if you look at this question, you will see that what I asked was what's the complementary event of probability of x greater than or equals to 1? So x greater than or equals to 1 obviously embodies when you have 1, 2, 3, and so on. So if you look at all this, the only thing that is missing here is 0. So probability of 0 will be the complement of this. So you go on now to find this expression. And that will be 1 minus probability of x equals to 0. That's what you'll be finding because this right here, this x less than equals to 0, is the complement. This is the complement of this event. So if you subtract this from 1, you'll be getting this one. That's the concept of complementary event. The addition of this probability plus this probability must give you 1 because they are complementary events. This is the complementary event of this. So that's the way you solve this. So 1 minus probability of x equals to 0. So you go on to find probability of x equals to 0, and obviously that will be e raised to power minus lambda here is 1.5. I prefer to use a bracket when I'm solving expressions like this. So 1.5 raised to power, your hex here is 0, all right, or 0 factorial. So this would be 1, that will be 1 minus e raised to power minus 1.5. The reason is because 0 factorial will be 1, 1.5 raised to power 0 will be 1. So all this will turn to e raised to power minus 1.5. So you solve this, you should get an answer of 0.7769. It's that simple. It's that simple. Sincerely, guys, this all it entails is so simple. You don't need to worry about anything. Just keep solving. You can't go wrong. Now, look at this next question. If probability of 2, now, guys, I need to tell you guys this, that even though I told you that probability of x equals to x, this is how we used to write it, or sometimes it's written as probability of capital eta x, all right? So it's not every time you would see it this way. So when you see something like probability of 2, it's still saying it this way. So it's almost like, if they say probability of 3, it's almost like saying probability of x equals to 3. So understand nomenclatures. It could be written this way also. So you need to note that. So we are told now that probability of 2 is equal to probability of 3. We have to find the value of lambda. Right? This is all word problems, technical questions. Of course, that you will only be able to solve if you have prior understanding of the whole concept. So if you don't have it, this would look difficult, but it's not difficult at all. What do you have to do right here? Of course, you have to go on to bring out all the values for your the values for what is P2. That will be x being 2. So it's more like writing probability of x equals to 2 because probability of x equals to 3. All right. So if you see this, you go on to fix in your values. That will be e raised to power, you don't know your lambda, e raised to power what? Minus lambda, lambda raised to power what? 2 over 2 factorial equals to e raised to power minus lambda, you don't know it, lambda raised to power 3 over 3 factorial. Can you go on to solve this and let's see what you get? Okay, so what did you get as the answer here? So obviously, if you understand this very well, you know that this will cancel this, obviously. Then you're left with what? Left with lambda. If you go on to divide both expression by lambda square. I'm sure you know that lambda square will cancel lambda square here. This will be left with just 1 lambda. So what you're left with here is 1 over 2 factorial equals to, you'll be left with only one lambda here. That will be lambda over 3 factorial. So this will be lambda 2 factorial, which is 2 times 1. 2 lambda is equals to what? 3 factorial. 3 factorial times 1, that will be 3 times 2 times 1. You understand what 3 factorial is? So you go on to divide both sides by 2. This will cancel this. So your lambda here is equals to 3. All right? So it's that simple. It's that simple, guys. If anybody tries to threaten you with probability distribution function, it's not worth it. It's very simple. It's very, very simple. So the only key is what I've tried to explain. Make sure you understand the basics and you understand the features of the distribution. You can't go wrong if you really understand the features. Now, look at this question. You can take it down. Let me try and dictate. Of course, I'll try and write also, but if you need to work very fast. So 1 nanogram, this was the question I read at the beginning of the class. 1 nanogram of plutonium, look at it right here. 1 nanogram of plutonium 2,3 now. Obviously, this is a content for radioactivity. Have an average of 2.3 radioactive decays per second. All right. And the number, okay, I don't need to say that. What is the probability that, this is the question now. What is the probability that in a 2-second period, there are exactly 3 radioactive decay? All right, so if you pay attention to this question, the question said 1 nanogram of plutonium 239 have an average of 2.3 radioactive decays per second. What is the probability that in a 2-second period, there are exactly 3 radioactive decay? So I would like you to solve this just 2 minutes. Let me see. It's very simple, but there is a technicality in it that you have to, I explained already, so you have to just make use of what I've said already. Okay, and the subsequent question under it, still on this question, said find probability that there are no more than, you have to find the probability that there are no more than 3 radioactive decays. So I'm just trying to be, so this is the first question said find probability that in a 2-second period there are exactly 3 radioactive decay. Now, let me try and solve this. And those of you that are approximately, you are making approximation to probably 2 decimal points. I'll caution you, as I said already. Always try and give your answers as much as possible in 4 feet, in 4 decimal points, because you never can tell what your truncating of those values will do, especially if you're going to be reusing that in a different calculation. Always try as much as possible to always tender your answers in its raw form as much as possible. Don't truncate too much of it. The second question is still in line with whatever was said in the first question. So find probability that in a 2-second period that there are no more than 3 radioactive decays. Look at what we have right here. 1 nanogram of plutonium-239 have an average of now. The reason why these kind of questions, if you're not very vigilant, you'll be thinking that this use of the word 1 here has something to do with the question. It doesn't have anything. This is just a word problem. It's more like saying 1 nanogram of plutonium. So I believe this is an element, whatever, those of you that are very good in chemistry, you know whatever this may be. So this is probably a constant of probably a nuclear or something, whatever. So 1 nanogram of that element has an average of 2.3 radioactive decay per second. Notice the word per second in this case. So the lambda per second, when you're dealing with per second, lambda here is 2.3. But note that this is for 1 second, because you can see the word per second. Let me use the same bracket. You can see the word per second there. So this is for 1 second. So the question said, what's the probability that in a 2-second period, now this is different now. This is not the same per second. This is in a 2-second period. So there are exactly 3 radioactive decay. In this case now, you can obviously see that your lambda here can no longer just be 2.3 when you're trying to solve this question, because you're dealing with a 2-second period, not 1 second. So your lambda has to be modified as 2.3 times 2. This will work for 2 seconds. So this is the rate for 2 seconds. Of course, that will be 4.6. Whereas this is the rate for 1 second. Now, this question said you should find the probability that in a 2-second period, there are exactly 3 radioactive decay. In this case, now you can see that your hex will be equals to what? 3. Because they said there are exactly 3. Exactly 3. Right? So what you have to do, of course, you have to go on to recollect whatever your PMF is. Probability of x, I'm writing this so that you get conversant with the fact that it can be written this way also, is e raised to power minus lambda raised to power x over x factorial. So you're trying to work for when x was 3. So you are going to find, again, I'm writing it this way so that you are also conversant with it. So as much as we can write it as p of x equals to 3, we can also write it this way. So this will be e raised to power, our lambda here will be 4.6 because you are dealing with the 2-second period, minus 4.6. Then we have 4.6 raised to the power of what's our x? Our x is 3 over 3 factorial. So if you go on to press this on a calculator, I'm sure you should get an answer of 0.163. All right. So you can see exactly how this works. Very simple. The key, which you guys could have noticed, is understanding the basics. Once you know the basics, you can crack any question without having any issue. So you see the second question we have here said probability that there are no more than. That means when you see the word no more than, what comes to mind? What's another way we can say that? At most 3. At most 3. So another way of saying no more than 3. No more than 3. Saying at most 3. At most 3. So when you're trying to find for at most 3, that means you're interested in probability of 3, but you're also interested in probability of 3 because you're also interested in probability of 2. We said no more than 3. It can be less than 3, but it should not be more than 3. That's the only case. It can be less than 3, but it should not be more than 3. So you can have for probability of when it was 1. Then don't forget, this is one part I've been stressing on. Always add up that of 0 also. It's part of the whole thing. 0 is not exempted, even though in some cases this 0 will bring in just a very small addition, but it matters a lot. All right. So this is what you have to go and solve for to get that answer. All right. So if you go on to solve for this, I believe for that of probability of x being 0, you should get an answer of 0.010. For that of 1, you should get 0.046. For that of 2, you should get 0.106. For that of 3, which we have done before, you got 0.163. So if you add all this up together, what's the answer that you'll be arriving at? Of course, you'll be arriving at an answer of 0.326. How many of you got this answer? Let me check the comments. Okay. Okay, so you can see you did not add for 0. So once you start omitting all these, not adding 0, you'll be having, and I want you to understand that in a theory question where you'll be told to solve something like this, they may be very strict with the decimal point because they know that if you don't add for 0, it will have an influence. So they may want to be very strict on the decimal point. So make sure you add for 0, very key. And even in your solution, they may want to penalize you for not adding for 0. So don't always forget that. So guys, this is where we're going to stop for Poisson, but we are going to delve into a bit of geometry. Geometry is too simple, very simple, but different. Very simple, but very different from every other thing we have talked about. And I'll be pointing out the difference in a moment. So guys, first of all, take a deep breath. How do you feel right now? We have completed 3 out of 4 of the probability distribution function. How far? How do you feel? So far, so good, right? Okay. You guys said, okay. Okay. A lot. Okay. Okay. So great. You guys are understanding it. Okay. 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 Someone is talking. Oh, someone is talking about variance and mean. I told you guys already what the variance and mean of Poisson is. It's it's lambda. Lambda is the variance. Lambda is the mean. The mean and variance is the same. Lambda, lambda. So your lambda is always going to be the mean and the variance. So guys, let's get quickly into geometric. All right. So of course we're going to have a class where we're going to still solve more questions on all these many things. But I'm trying to give you guys a very good introduction. I want to spend this moment to give you proper introduction to every one of these. So we're going to be playing with lots of questions, right? And somebody that was talking about the recollection of formulas as being a problem. Of course, that could be a problem to everybody. So what we all do is that we go on to practice more. So if you want to really uh, if you want to really understand and not forget the formulas, what you have to do is always practice enough. So let's quickly get into geometric distribution. Now, geometric distribution is, as I said, it's different. Geometric distribution is different, and you need to understand the uniqueness of geometric. So don't get it wrong. Make sure you pay attention, please, because so that you don't get hooked up in geometry. Again, we're going to practice more questions in a later class because of time. But we're going to give a very proper introduction. As you know, I would not want to rush this at all. So let's get right into it. The difference between geometry and every other distribution we have been talking about is this. Every other distribution was always trying to find the number of success. So in every other distribution, we're saying we called X the number of success. If you recollect, that was what we have been doing. You see this Poisson, we say, what's the probability of getting 3 radioactive decay? We said X, probability of X equals to 3. That was how we were going about these things. But you see, in this distribution, geometric, now we are under geometric. Please put in mind, we're under geometric. This is for all the previous one. We're dealing with X as the number of successes. But in this case now, geometric distribution is distribution of the number of trials needed to get the first success in repeated independent Bernoulli trial. Let me just explain it in a nutshell. What geometric calculates? Geometric distribution will say, come, I want to find a head. I'll give you a coin. And I say I want to find a head. Please toss a head. So now, whereas binomial is saying, in you toss getting a head, there are 2 outcomes and every other thing. All right. You see, under geometry focuses on something else. What geometry focuses on is, well, you keep tossing that coin. You toss it the first time. You toss it the second time. Geometry says, how many trials did you have to make before you got the first success? So if you're looking for a head in tossing a coin, geometry is saying, how many times did you have to toss that coin before you got head? So the distribution that mirrors, models that experience is geometric. That's the advantage of geometric. Like take for instance, you are playing a Ludo game. So you needed a 6 to start. So when you are tossing the die up and you're looking for a 6, what geometry is doing there is to model what's going on. Okay, I'm looking at this guy. He's trying to get a 6. He tossed it up the first time. He tossed it up the second time, the fourth time. Oh, it took him 6 trials before he got a 6. That's what geometric does. Geometric, as I said, is the distribution of the number of trials. Geometric is the distribution of the number of trials needed to get the first success. In repeated, you see the word there, repeated, independent. This is very key. Every of these trials must be independent. Bernoulli. This is just trials. You see the use of the word Bernoulli here is because each of, when we say Bernoulli, you should know the English. This Bernoulli has to do with one trial. So when we said N is to get the first success in repeated independent Bernoulli trial. For each of those trials, one of them, when we're dealing with just one trial, we're seeing it as a Bernoulli. So this word here is just a placeholder there to tell you that each of the trials, of course, follows each one. When you're dealing with one of the trial, it follows a Bernoulli distribution. So geometric is the distribution of the number of trials needed to get the first success. That's what it does. See, geometric ends when you get your first your success. Geometric is not interested in you getting, when you are tossing a coin up 5 times, I got a head up 2 times. When I tossed a die up 10 times, I got a 6 3 times. Geometric is not interested in all those ones. The moment you get your success, geometric is done. That's the work of geometric. Geometric models only the number of trials you needed to do. All right. Geometric models what you do once you got that first success. That's all. It's out. Once you're done with the success, once you get the success, it's done. Now, of course, this you obviously know that the PMF will be quite interesting. All right. Very, very interesting, because this is different from the rest. Now, let me first start by saying X here will not represent number of successes and all those things you had in the previous one. X here represents the number of trials, the number of trials needed to get the first success. That is geometric. When you're doing geometric, don't forget your X here is not the same thing as the other ones. So please take note of that. Now, how do we then model the PMF? Now, let's use, of course, that was the reason why I gave you the way of getting it, and I didn't want you to just be cramming. If you follow through on what we were saying when we were dealing with Bernoulli, I told you the logic around finding the PMF. I said it was like probability of success raised to power number of success, then probability of failure, which is Q, or 1 minus P, raised to power number of failure. This was for Bernoulli. And what we were doing for binomial, what changed was just this place as n, and then we counted each of the events using the combination. If you remember when I explained all this. Now, look at what we are having here. In this case now, we told you that X represents the number of trials needed to get the first success. Of course, in this case, our P will be representing the probability of success as before. P will be the probability of success. And Q, which is equal to 1 minus P, is obviously going to be the probability of failure. You need to remember this, very important. Now, if you're going to have your PMF, let me just write it so that you'll be able to see it. Look at it. It's going to have, this is going to be what your PMF will be. Probability of failure raised to power X minus 1 and times P, just times P. Now, if you look at this, you would see that this is so intact because X represents the number of trials we had to go through. The number of trials we had to go through before we got our first success. So let's say, for instance, that it took us 10 trials before we got our first success. So what does that mean? That means the person previous 9 trials were failure. Now, let me repeat that again. Let's say you were tossing a coin and it took you 10 trials to see a head. Now, I told you what geometric does. It mirrors the number of trials it took you to get the first success. So if it took you 10 trials, that means 9 of the previous trials were all failure. That means the number of failure in that case was 9. Now look at this PMF. I told you it's more like saying probability of failure over number of failure, probability of success over number of success. Now you see why we only have P raised to power 1 here. because your number of success in a geometric will not exceed 1, because I told you geometric terminates once you get your first success. So you cannot have 2 success. That's why you see your number of success here, which I don't need to write, is raised to power 1. It's more like saying, as I said already, probability of success raised to power 1, raised to power number of success, probability of failure raised to power number of failure. So all these things will help you to recollect this formula easily. You cannot have your number of success in a geometry cannot be 2, cannot be 3, cannot be anything other than 1. It must be 1. So that's why your PMF is having it as this. Now, 1 minus P, this is your probability of failure. Now, what will be your number of failure? Your number of failure will obviously be whatever the number of trials you had to do, which was X. Don't forget, I told you X represents the number of trials. So if your number of trials was 10, you will be saying 10 minus 1. That means because 1 was the success, but this was the success. This is representing the success now. So if you had 10 trials to get success, just subtract 1 from it, which was the one that you got successfully. That will be the number of failure. Can you guys flow with that? So if it took you 18 trials to get to success, that means 17 trials were failure. So if it took you 18 trials, that means number of failure will be 17. You can see that this PMF models it properly. So just subtract 1 from the number of trials it took you to get your first success. You'll be able to get your number of failures that happened. So if you are tossing a die and you threw the die up 7 times, and it was at the 7th time you got a 6, which was what you were looking for. So if it took you 7 trials to get the first success, 7 trials to get the first success, that means you failed to get the first success 6 times. And you can see right here, that will be 7 minus 1. It took you 7 times. X represents the number of trials it took you. 7 minus 1, that will be 6. All right. So this is the PMF of a geometric distribution. It still follows the same pattern I've been explaining all this while. Good. I believe you guys could understand everything I just said. All right. So now the next question is, what's going to be the range of value for your X? Because that's always very important to state when you're trying to state the PMF. So your X must be, of course, you don't know the number of trials. Of course, it could not be 0 trial. So 0 will never be here. Don't forget, when we're dealing with Bernoulli, we said X was 0 and 1. That means, don't forget, X here represented number of success. When we're dealing with binomial, X was representing number of success here. We said X was between 0 to n. When we're dealing with Poisson, we said X was 0, 1. We don't know the n because in this case, we don't have number of trials. But in this case now, our X represents number of trials. So we can never have 0 number of trials to achieve first success. It's not possible. We said X represents the number of trials needed to get the first success. It can never be 0 number of trials to get the first success. Now, it's very possible that the first trial got the first success. That's possible. So it's possible for you to have the first trial. That means you threw a die up, and at that very instance, you got a 6. That's possible. That's not impossible. That's very possible. So your value of X, that means the number of trials you will need to get the first success, will start from 1, 2, and you cannot say. You cannot say. So it's going to keep going. You cannot tell the band of this. So you cannot tell that this is still any number, because depending on this is if you keep throwing the die up 100 times and you have not seen the first success, this X will keep going. So X is 1, 2, and so on. But X can never have a value of 0 in this case. Don't forget again, X here don't represent just anything. X represents the number of trials needed to get the first success. All right, guys, I'm really sure you guys can flow. Now, one other thing you need to note, which you have always noted for every other one, you should know the mean and variance of every distribution. Bernoulli, we said the mean is P, the variance is PQ. All right, binomial, the mean is NP, the variance is NPQ. Poisson, we said the mean is lambda, the variance is lambda. Now, what about for geometric? The mean here is given as 1 over P, and the variance, which we see as sigma squared, is given as 1 minus P over P squared. Of course, this is p squared. Of course, the variance would have been q over p squared, because you know that 1 minus p is obviously q. So you have to note this. This is the mean and variance of a geometric distribution. Mean is 1 over p. Variance is q over p squared. All right. So we are almost done with the class. Let me solve just one question so that you guys can understand what we're doing. Please take this question down. This is going to be where we're going to stop. After this question, please pay attention really hard, because I just really want to have something for you to lay hold on before we call it a close. In a large population of adults, this is the question right here. In a large population of adults, 30% have received CPR training. Now, if adults are randomly selected, I'm going to give you an assignment. This is the one we're going to solve, and I'll give you an assignment, hopefully. If adults from this population are randomly selected, what is the probability that the sixth person sampled? Look at it now. This is the question. What is the probability that the sixth person sampled is the first that has received CPR training? So in a large population of adults, 30% have received CPR training. All right. If adults from this population are randomly selected, what is the probability that the sixth person sampled is the first that has received CPR training? So do you have an idea of that? Look at the whole question. This is a very typical example of where you would need to understand geometric distribution. So what you see to this, now you're told that you have a large population of adults. 30% have received CPR training. Of course, you should be able to identify what 30% here means. What does 30% mean here? Can anybody in the comment section give me the answer to that? If they say 10% have received CPR training, there was a large population of adults. They say 10% of that population have received CPR training. If adults from this population are randomly selected, what's the probability that the sixth person sampled is the first that has received CPR training? So first of all, when you see the word 30% there, that obviously is giving you the probability of success. That means for you to get the probability of success, that means successfully picking, if you say you have 100% of the population now, if you're going to pick, the probability of you picking somebody that has received CPR training is 30 over 100 because they say 30% have received it. The probability of success there will be 30 out of 100. So if you had 100 adults now, they said 30 of them, if you had 100, the meaning of 30% is if you had 100 adults, 30 of them has received CPR training. So now, that means that's probability of success here. That's 3 over 10, which is 0.3, 0.33. Sorry, just 0.3. Now, if adults from each population are randomly selected, what's the probability that the sixth person is the first that have received CPR training? You need to understand questions before trying to solve it. Nobody, notice from this, nobody told you that this is geometric or this is Poisson or this is binomial. All you're just seeing is obviously just an understanding of the direction of the question. They said, what's probability that the sixth person? That means it's more like saying you were having trials. You pick the first, you pick the second, you pick the third, you pick the fourth, you pick the fifth, you pick the sixth. You're now saying what's probability that that sixth trial was what gave you the first success. That means the sixth person sampled. Of course, this sixth person sampled, you have sampled 5 people previously. They did not give you, you were not able to catch anyone that received CPR training. They're now saying what's probability that the sixth one you picked was the first that has received the CPR training. This is a perfect geometric distribution where you are mirroring a situation where your first success happened at a particular trial. And the trial here they are saying is that on the sixth trial was when you got your first success. So when you sampled, you did the sixth trial. That was when you were able to apprehend someone that has received CPR training. All right. So looking at this now, that means, don't forget, X here don't represent number of successes, as I've been stressing. X here represents the number of trials needed for the first success. And in this case, the question said that number of trials that happened was 6. So probability of X equals to 6. That's what you are trying to find. What's the probability that the sixth person sampled? That means this is what you are trying to find. Probability that it was at the sixth trial that you got your first success. So this models a geometric distribution of which you know what the PMF is. But again, just as I love to do, let me repeat what the PMF said of geometric. So when you see something, once you see that something follows a geometric approach, one thing you need to always remember is what is the model for the distribution that this thing follows. So this obviously follows 1 minus p raised to power x minus 1. I mean, number of trials needed to get the first success minus 1. Of course, I explained that already. Then p raised to power 1. Multiply them together. That's your geometric PMF. So looking at this now, you can see that probability of x equals to 6 will be equals to your p is 0.3. That means your 1 minus p, which is q, will be 0.7. All right. So 1 minus p there, that will be 0.7 raised to power x here is 6. That will be 6 minus 1 multiplied by 0.3, which is probability of success. You have all the data there. So this will be 0.7 raised to the power of 5 multiplied by 0.3. All right. And if you do this, you should get a value of 0.0504. All right. So guys, quickly right now, can you push me the values for the mean, variance, and standard deviation of this question? What is the mean? What's the variance? And what's the standard deviation of this question? Can you give me the answer quickly? Those of you that have been following. So what's the mean, variance, and standard deviation of this question? What's the mean, variance and standard deviation of this question. Okay. Now, if you recollect what we have the mean as 1 over p. So mean is 1 over p. The variance is what? Q over p square. The standard deviation will obviously be the square root of whatever the variance is. So you have your p to be 0.3. So that means the mean will be 1 over 0.3. And that gives you a value of what? 3.3, right? 3.3, obviously. Q, which is 0.7 over p square, that will be 0.3 square. So if you have that, you'll be having it as 7.7, am I right? Okay. And the standard deviation will obviously be the square root of that. So standard deviation will be the square root of variance, obviously. That'll be square root of 7.7. You get an answer of 2.79 or thereabout. So this is the assignment I want to give to you now. All right. So the question is, please take it down. Still on this same question, it's still a continuation of this question. The question is, what's the probability that the first person trained what's the probability? So this is the question. Of course, it still follows this question. What is the probability that the first person trained in CPR occurs on or before the third person sampled? So this is the question for you to answer diligently. The question said, of course, based on this data you have been given initially, based on all this, what's the probability that the first person trained in CPR occurs on or before the third person sampled? So you understand that in this case now, they're asking you to find what? Of course, if you look carefully, on or before the third person sampled. That means in this case now, probability of x less than or equals to 3. On or before. So this is what you will be trying to find. On or before. Probability of x less than on or before. It can be on the third trial. That means the number of trials needed to get your first success could be on the third trial, or it could be before the third trial. That will be the second trial. It could be on the first trial. Don't forget there is no 0 trial here. It's not possible for you to have 0 trial. So you'll be having probability of x equals to 1 plus probability of x equals to 2 plus probability of x equals to 3 as your answer to this. You must not put that of 0. If you put that of 0, that will mean you don't understand the topic, because you can never have 0 trial to achieve the first success. So the probability, this is the mathematical expression of the answer to what we have here. So guys, how do you feel right now? We have come to the end of it was really great this weekend. I don't know about you, but I feel the message was passed very clearly. What do you feel? How do you guys feel about this topic? Can you give me your feedback in the comment section quickly? We have come to the end of so what's your comment? How do you feel? You feel really good, okay? Okay, good. That's good. So probability division function has come to an end. This is everything. There's nothing more. The rest is for us to keep tackling several questions that, of course, it's endless. You cannot tackle all the number of questions possible. Yeah, you just keep working. All right, great. I like the comment. Okay, so this is okay. This is where we're going to end the class right now because uh, I think we have done a great job. You guys, thank you very much for your contributions, your participation. It really means a lot. I love to know that you guys are being impacted. I love to know that you are understanding the topic properly. Make sure you do your best to practice more, expose yourself to more questions. At this point now, you are free to go on to solve loads of questions on this topic because you've known what you need to know, the basics. So, guys, thank you very much and prepare well for your tests and make sure you update your notes. Make sure you are intact. All right. It's all going to be great. Thank you, guys. Enjoy yourself. Good night. Bye bye.